Some people may say that there is no such thing as probability. After all, either an event will occur, in which case its probability is 100%, or the event will not occur, in which case the probability is 0%. But there is a way we can assign an objective definition to the word probability, in a way that conveys more than just our own personal ignorance of whether or not the event will occur. Suppose we repeat the same experiment, such as flipping a coin, an infinite number of times. The percentage of times that an event, such as the coin landing heads, occurs is what we will refer to as the probability of the event. If the coin lands heads 50% of the time, then we say that landing heads has a 50% probability. But with this definition, an event can still occur even if it has 0% probability, and an event is not necessarily guaranteed to occur even if it has 100% probability. For example, suppose we randomly pick any real number between 0 and 10, with every possible value having an equal probability. What is the probability that the number we pick ends up being pi? Well, since there are an infinite number of possibilities, the probability of picking this exact number has a probability of 0. There is also, therefore, a 100% probability that we will pick some number other than pi. Yet, the event of picking exactly pi can still occur. There are many cases like this, both in classical physics and in quantum mechanics, where there are an infinite number of possible outcomes for a measurement. In these cases, rather than talking about probability, it makes more sense to talk about probability density. For example, in this case, we would say that there is a 10% probability of picking a number between 0 and 1, a 10% probability of picking a number between 1 and 2, a 10% probability of picking a number between 2 and 3, and so on. In this particular case, the probability density is represented by a rectangle, due to the fact that every possible outcome has an equal probability of being selected. If, on the other hand, some possible outcomes are more likely than others, the probability density will no longer be a rectangle. In this example, the closer a number is to the number 10, the more likely it is to be selected. In this other example, the closer a number is to the number 5, the more likely it is to be selected. The probability of the number being between any two particular values is always represented by the area under the probability curve between these two numbers. A probability curve with this particular bell shape is extremely important both in classical probability and in quantum probability. To see why this is the case, suppose we take a coin and we flip it 2 times. One possibility is that the coin will come up heads both times. A second possibility is that the coin will come up heads the first time and come up tails the second time. A third possibility is that the coin will come up tails the first time and come up heads the second time. A fourth possibility is that the coin will come up tails both times. Each of these 4 possibilities is equally likely. In one of the 4 outcomes, the coin lands heads twice. In 2 of the 4 outcomes, the coin lands heads only once. And in one of the 4 outcomes, the coin lands heads 0 times. In one of the 4 outcomes, the coin lands heads twice. In 2 of the 4 outcomes, the coin lands heads only once. And in one of the 4 outcomes, the coin lands heads 0 times. We therefore have a 25% probability that heads will come up twice. We have a 50% probability that heads will come up exactly once. And we have a 25% probability that heads will come up 0 times. Let's create a graph that represents this result. Now, let's suppose that instead of flipping the coin twice, we flip it 3 times. Now we have 8 possible outcomes. In one of the outcomes, the coin lands heads all 3 times. In 3 of the outcomes, the coin lands heads twice. In 3 of the outcomes, the coin lands heads once. And in one of the outcomes, the coin never lands heads. As before, let us create a graph that represents this result. Let's have the y-axis represent the probability, and let's have the x-axis represent the percentage of times that the coin landed heads. Now let's repeat this experiment, but instead of flipping the coin 3 times, we flip it 4 times. Now the graph looks like this. Now let's flip the coin 5 times. Six times. 7 times. 8 times. 9 times. 10 times. Now, let's flip the coin 100 times. Now let's flip the coin 1,000 times. Now let's flip the coin 10,000 times. There are 2 very important results to be learned from this. The first result is that the more times we flip the coin, the more likely it is that the percentage of times that the coin will come up heads will be exactly equal to 50%. The second important result to be learned from this is that if we flip the coin a large number of times, the graph we generate will look like the bell shape that we saw earlier. Let us return to the case of the rectangular probability density, where every number between 0 and 10 had an equal probability of being selected. Suppose we plan on picking 1,000 numbers using this probability distribution. Suppose that we then plan on taking the average of these 1,000 numbers. Suppose we need to predict what this average will be. This is similar to flipping a coin 1,000 times and needing to predict the percentage of times the coin will come up heads. Just as we created this probability distribution for flipping the coin 1,000 times, we can similarly create a probability density for the average of the 1,000 random numbers. Although the probability distribution for flipping just a single coin is a simple rectangle, The probability distribution for the average of 1,000 coin flips is a bell curve. In exactly the same way, although the probability density of picking just a single number is described by a simple rectangle, the probability density for the average of 1,000 of these numbers is a bell curve. This curve shows that there is a very small probability of the average being close to 10 or being close to 0. It is far more likely that the amount of numbers we pick that are close to 10 will be roughly equal to the amount of numbers we pick that are close to 0, and hence their average will be close to 5. This is why this curve shows that having an average of 5 is the most likely outcome. Just as in the case of flipping a coin a large number of times, we ended up with this bell curve. Now suppose that instead of picking 1,000 numbers, we pick 10,000 numbers. As before, we need to predict what the average of these 10,000 numbers will be. Just as we created a probability distribution for flipping the coin 10,000 times, we can similarly create this probability density for the average of the 10,000 random numbers. As with the case of flipping a coin a large number of times, the more numbers that we select, the higher the probability that the result will be at the center of the curve. This is due to the fact that the more numbers we select, the more unlikely it is that they are all simultaneously close to 0, or all simultaneously close to 10. Let us suppose that instead of starting out with the rectangle probability density, we instead start out with the triangular probability density. Suppose we again plan on picking 1,000 numbers, but this time using this triangular probability distribution. As before, we plan on taking the average of these 1,000 numbers, and we need to predict what the average will be. As it turns out, the probability density for the average of these 1,000 numbers will again have a bell shape. But this time, the center of the bell curve will be shifted from where it was in the previous example. This is due to the fact that with the triangular probability density, numbers closer to 10 are more likely to be selected, and the average of all these numbers is therefore most likely going to be closer to 10. Now suppose that instead of using the triangular probability density to pick 1,000 numbers, we use it to pick 10,000 numbers. The probability density for the average of all the numbers will then change to look like this. As it turns out, the two results that we saw in the coin toss are actually universal rules that apply to everything. Regardless of what probability density we start out with, we will always end up with a bell curve when we take the average of a very large number of samples. This is why the bell curve is so critical in probability and statistics. Also, in all cases, the probability that the average of all the numbers will be exactly at the center of the bell curve approaches 100% as the number of samples gets bigger and bigger. In other words, the more random samples we have, the more unlikely it becomes that their average will vary even slightly from the value that we expect it to be. Even if we start out with an inherently random process, the average result always becomes more and more deterministic as the number of samples increases. What we are typically able to observe in the universe around us is the average of the behavior of a very large number of subatomic particles. Although each of these subatomic particles is governed by the probabilistic laws of quantum mechanics, their average behavior becomes more and more predictable as the number of particles increases, just as in the examples we saw here. This is why much of the universe that we are able to observe can be predicted through the deterministic laws of classical physics, even though the underlying physics of the subatomic particles is described by the probabilistic laws of quantum mechanics. Much more information is available in the other videos on this channel, and please subscribe for notifications when new videos are ready.